You might recall in first year chemistry, you learned about several broad categories of chemical reactions that go to completion. You had your composition reactions, sometimes called your synthesis reactions, where you're making a compound where two elements or an element and a compound or two compounds become one. You also had the opposite of that, which was your decomposition reactions, where you had one compound that broke apart into two compounds and or elements. Then you had your single replacement reactions or single displacement reactions, and you had your double replacement reactions. Chapter 3, and this is lesson 3, is focusing on your double replacement reactions. Many of them are represented by the following examples. You have the combustion reactions, and the combustion reactions are actually a combination of several of the categories above. Then you also have your precip reactions, the ones that make a solid. We did that in the last lesson as well. This time we're going to be talking about acid-base reactions. And we're also going to be talking about the kinds of reactions in the next unit, or I should say the next lesson, that are redox reactions. But the other one in this particular lesson is going to be the reactions that produce gases. So our focus in this lesson are going to be these two, acid-base and gas-producing reactions. That's not to say that some of these others, like decomp, aren't going to produce gases, because they will. All right, having set the context, let's focus in on acids and bases. Now, I've broken this idea of acids and bases into 4 categories, 3 of which are chemical definitions, and 1 of which is sort of a colloquial or an everyday definition. So what I'm calling the first definition of acids and bases is actually not necessarily a chemical definition about what's going on at the particle level, but is more the everyday definition that was formed well over 100 years ago, probably in the 19th century at least, where they recognized there were some chemical reactions that produced lots of gases, like carbon dioxide or maybe hydrogen gas. Also, these compounds that would produce gases when they're mixed with metal compounds like metal carbonates or metals themselves. Here's your metal carbonates and here's your metals. These compounds also had a sour taste. Now, right off the bat, you would recognize you have no business doing a test to see if something is an acid or not by tasting it. But there were in foods things that were acidic in that they produced gases like hydrogen gas when reacting with a metal that did taste sour. There were some foodstuffs. And a good example would be the acetic acid that you would find, for example, in dill pickles. Lots of other fruits can also have a sour flavor. Then another thing that they recognize is that these same solutions that could produce bubbles of gases and had a sour taste also would turn litmus paper a particular color. And you should know what litmus paper is. You should know what the color change in litmus paper means. If we have red litmus paper, or if we have blue litmus paper, or we have neutral litmus paper, what does it do? Well, blue litmus paper is going to turn one color, and red litmus paper is going to turn another color. So it turns blue in a base. If red litmus paper will turn blue in a base, and Blue litmus paper will turn red in an acid. And here's how I remember that. It turns blue in a base, and it turns red, last letter D, in an acid. And then a neutral litmus paper would have two compounds dissolved and dried into the paper, so it could turn either color, red in an acid or blue in a base. And you should know that test. That should be common knowledge for a chemistry student. Another thing that they learned is that acids and compounds called bases would neutralize each other. And the neutralization of an acid and a base basically produces a salt water of some type. Now, when we think about neutralizing, if you think ahead to what you know about pH, an acid and a base does not always give you a neutral pH, that is to say, a pH of 7. If you have a strong acid and a weak base, you're actually going to get a pH less than 7 in the acidic range. If you have a strong base and a weak acid, you'll get a pH greater than 7 in the basic range. If you have a strong acid and a strong base, then you can get a pH at 7. If you have a weak acid and a weak base, it's a little bit more complicated. You would have to compare the equilibrium constant for the acid and the equilibrium constant for the weak base and see which one is bigger. And we'll get to that much later in the book when we get to equilibrium second semester. So this is kind of like an everyday, ordinary definition of acids and bases. Bases would be bitter if you're using the taste test. And again, you shouldn't do that. Another thing you should avoid is that if you get an acid spilled on you, you don't necessarily want to run around and find the nearest base to dump on it in order to neutralize the acid. If you spill some acid or base on you, the best thing to do is to use lots and lots of water. And of course, if you're a student, make sure you tell the teacher. Now, definition number 2 is going to be one by Svante Arrhenius, and that's often considered the first definition from a chemical perspective, or at least with a chemical explanation in terms of the particles for acids and bases. Then we'll talk about the Bronsted-Lowry definition, and then later there is the Lewis definition. So let's look at the let's look at the Svante Arrhenius definition of acids and bases. Svante Arrhenius, you can see that he got into his chemistry in his just before the beginning of the 20th century and on into halfway through the 20th century. He grew up in a Lutheran home, but somewhere around the age of 15, this Swedish gentleman at some point abandoned his upbringing and became an atheist. And we don't know much about any reason why or what experiences might have provoked that or what his thinking was. In any case, we're going to be looking at the Arrhenius definition of acids and bases. Like I said, he was a Swedish chemist, and in looking for an explanation at the particle level of what makes an acid and what makes a base, he focused in on the idea that acids make hydronium ions, and we'll write it like this. Keep in mind that oftentimes in chemistry books and chemistry lectures, these two terms, aqueous, are used interchangeably. But if you think about what an H plus is, an H plus is nothing more than a proton. And a proton, of course, would be a very, very concentrated charge on one particle. So the possibility of a single proton existing all by its lonesome in a watery environment would be practically zero. So that proton would almost instantly be attracted to a water molecule. And I like to write the water molecule, especially when I'm talking about acids and bases, as HOH. And this becomes H3O positive, the hydronium ion. In college or university, you may get a professor or you may have an author of a textbook that is adamant that you always represent the hydronium ion like this. You might have another professor or textbook that says, as long as you know what you're doing, it's okay to represent the hydronium ion like an H+. And when it comes to balancing equations, if you are using this form, it just means you need to add a water molecule to the other side of the equation in order to completely balance the equation. So that's pretty much up to you. I'm kind of flexible. I hope that you understand the difference between an H plus and an H3O plus, even if you choose to use them interchangeably. All right, before we turn the page, let's take a look at these pictures here. And especially picture number 3, red cabbage. If you take a piece of red cabbage, it's actually more purple, I think, and you kind of grind it up and put it in hot water, you can use that liquid water, especially when it cools down, to pour it into different solutions, different substances that you've dissolved, say from around the house or around the lab. And you get this full range of colors. And it's very pretty, and you can do some dramatic demonstrations even, for your siblings, or if you're teaching a Sunday school class or a vacation Bible school class and you want to demonstrate some colors for whatever reason. You can find household products that are clear when you put them in, dissolve them in water or pour them into water, but then when you add this red cabbage juice, you can get these distinctly different colors. Here's a good example of a metal reacting with an acid to produce hydrogen gas, particularly hydrochloric gas. And over here, calcium carbonate is all over the place. We've mentioned frequently that calcium carbonate in its metamorphosed stage or form is called marble. In its sedimentary form, it's called limestone or chalk. You can also have coral that makes up the shells of a lot of sea creatures like coral. All right, moving to the next page. I mentioned in the previous screencast that the best way to know what is a strong acid and what is not a strong acid is to simply memorize the strong acids. And there are 6 of them. 3 of them are halogenic acids with chlorine, bromine, and iodine. And then you've got nitric, and you've got perchloric, and you've got sulfuric. Certainly the ones that you're most commonly going to encounter in everyday chemistry is sulfuric and nitric and hydrochloric. But if you know those 6 acids, then any other acid that you encounter will be a weak acid. As far as your bases are concerned, depending upon your textbook, the list of soluble strong bases might vary a little bit. But in terms of strong bases that are soluble, you'll notice these are all ones that come from the first and second columns in the periodic table, like lithium, sodium, potassium. These are soluble and they are strong bases. You'll notice they're also hydroxides. And any other base is going to be a weak base and will probably be also very weakly soluble. Now, when it comes to a very important weak base, let's look at ammonia. And you might say, well, ammonia is NH3. And I put that question mark there because, so where's the hydroxide in ammonia? Remember, the Arrhenius definition is all about aqueous environments. In fact, that is its major limitation. Common test question. The weakness of the Arrhenius definition for acids and bases is it's limited to aqueous solutions. When we get to the Bronsted-Lowry definition, that's no longer the case. It works in non-aqueous environments as well. So why is ammonia a weak base? It's because when you combine it with water, the water donates a proton, if you use the Bronsted-Lowry definition, and there's the hydroxide. So Arrhenius definition would focus on the presence of these. You made a hydroxide in water solution, just like you made hydroxides appear in water solutions. The water yanked them apart. So you had free floating or dissolved hydroxides. Ammonia does the same thing. So by the Arrhenius definition, it is a base. Now the Bronsted-Lowry definition will say, oh look, water is donating a proton to the ammonia molecule. So therefore the ammonia molecule is receiving a proton, which makes ammonia the Bronsted-Lowry base, and it makes water, in this case, a Bronsted-Lowry acid. So you can see that in this case, the ammonia is both a Bronsted-Lowry base and an Arrhenius base. It's both of those at the same time. Your focus, your emphasis, just different depending on the definition you're using. So Arrhenius would say an acid is a substance that when you dissolve it in water, you get more H pluses. And here we have a good example of hydrochloric. And this is not a decomposition. Remember, you've got your aqueous here. It's not turning into hydrogen gas and chlorine gas. This is all in a water environment. So you are bubbling hydrogen chloride gas into water, and you are getting hydrogen ions and chloride ions. You could also go like this, add a water molecule over here, in which case instead of that you would put H3O+. And some professors would prefer this way, the one that I just modified with the blue, preferable over the one that was on the page before I marked it up. A base is something that produces hydroxides. Sometimes you know it will because you can see it in the formula. But in the case of ammonia, of course, you couldn't see it in the formula. Nevertheless, in a water solution, it produced hydroxides. Then, the other pattern that you should remember about acids and bases is that an acid plus a base always produces a salt plus water. Now, that does not mean that the pH of this salt water solution is going to equal 7. That's only true if your acid and your base are strong. In this case, a neutral solution would have a pH of 7 because hydrochloric and sodium hydroxide are strong. And you're going to get a strongly soluble salt in the process. And so the strongly soluble salt would completely dissolve into its sodium and chloride ions. And when you go to write your net ionic equation, you're going to see that your chlorides are going to cancel out because a strong acid will dissociate, a strong base will dissociate into its sodium and hydroxide ions, and those sodium ions will cancel out, and the only thing that's left is your H plus and your OH minus produces water. And that is the net ionic equation, NIE, every time for a strong acid and a strong base. If you're taking a test and you're asked to write what is the net ionic equation for this acid and base, and you identify the acid and base as being both strong, don't go through the whole process of writing out the balanced equation and then writing out the complete ionic equation, unless, of course, the instructions say to. Just go right ahead and write H plus OH minus gives you water. Now, of course, if you have a weak acid and a strong base, the strong base is going to win out and your pH is going to be greater than 7. And if you have a strong acid and a weak base, the strong acid will win out and you're going to have a pH less than 7. And the reason for this has to do with something that we call hydrolysis. The hydrolysis of the conjugate of the weak acid or the hydrolysis of the conjugate of the weak base. And again, that's language and explanation that we will worry about when we get to a more detailed study of acids and bases when we talk about titrations and buffers in the second semester. Also keep in mind, of course, that strong acids and strong bases will completely dissociate, assuming there's enough water, and weak acids and weak bases will not completely dissociate even if you have a lot of water. Obviously, if you have 57,000 gallons of hydrochloric acid and you dump it into a couple gallons of water, not all of your hydrochloric is going to dissociate. Now, our third definition is a more comprehensive definition because it works even if you don't have an aqueous environment. Sometimes we talk about other kinds of environments. You can even have environments in a vacuum, which I had to learn an awful lot of the chemistry that takes place in a vacuum similar to outer space. And we would duplicate outer space as best we could using a vacuum chamber that would have pumps pumping the air out of it. And those pumps had to be on for 24/7 and day after day just to get a vacuum that might be maybe within a factor of 1,000 as good as the near vacuum that outer space is. Remember that outer space is not a perfect vacuum, no such thing. Outer space has approximately 1 particle per cubic centimeter. So if you were to draw a cubic centimeter and imagine that it's space, you would have 1 particle, maybe an electron or a nucleus inside that. So that's basically the concentration of a near perfect vacuum in outer space. The best we could do in the lab, and we needed a vacuum as good as we could get in the lab that I was doing to do the chemical weapons detection. Even so that we could detect extremely small amounts of chemical weapons, we needed to have as close to a great vacuum as we could. And the best we could do was maybe 1,000 times more particles per cubic centimeter than this. Nonetheless, that still isn't very much at all. When you consider a cubic centimeter, for example, of water, and you should know this, which is the same as 1 milliliter of water, which would be 1 gram of water, which would be 1/18th of a mole of water, because a mole of water is 18 grams. And 1/18th of a mole of water would have 6.022 times 10 to the 23rd particles divided by 18. And so you can see that you are talking about a very, very, very large number of particles of water in 1 cubic centimeter of water. So 6 times 10 to the 23rd divided by 18 is about 10 to the 22nd. And you could say that basically is almost a 1/10 of maybe a trillionth, because a trillion would have 12 zeros. A trillion particles of water in a cubic centimeter. So, the Bronsted-Lowry definition focuses on protons. And I mention this because later in the book, when they talk about the Lewis definition, you might remember the Lewis dot structures, when we would use dots to represent electrons, like the dot structure for carbon. If we filled each orbital with 1 electron, it looked like that. Well, this same guy, Gilbert Lewis, his definition focuses on electrons because that's what he was always thinking about, were electrons. So Lewis' definition is going to be about gaining and losing pairs of electrons. So we'll talk about electron pairs later. Whereas the Bronsted-Lowry definition is going to focus on the gaining or losing of a proton. So in the Bronsted-Lowry definitions, and some books you're going to see these words reversed. For example, if you're English, you're going to go with the Lowry-Bronsted definition because Lowry was English. And if you're Danish, you're going to go with the Bronsted-Lowry definition because Bronsted, if I'm pronouncing that Danish correctly, he's Danish. And here the focus is on protons. So an acid is going to donate a proton, and a base is going to accept or receive a proton. So if you think about the word donate has the letter D, and donor or donate has the letter D. Acid has D, donor has D. Bronsted-Lowry acids donate a proton. They lose a proton. And bases are going to therefore receive that proton. Now, when we come to talk about the Lewis definition, it's just the opposite in two ways. Instead of protons, we're talking about electrons, but instead of donating and losing, we're talking about losing and donating. So a Lewis acid compared to a Lewis base, whereas a Bronsted-Lowry acid donates a proton, a Lewis acid is going to receive a pair of electrons. And the Lewis base is going to be donating the pair of electrons. And it's easy to understand why. If you take the nitrogen atom and then you turn it into ammonia, you'll notice that right here you have a lone pair of electrons. So if that nitrogen donates that lone pair of electrons, it's acting like a Lewis base if it donates that pair of electrons to, let's say, a hydrogen nucleus. A hydrogen nucleus, which is just a proton, which would want 2 electrons in its outer shell. So these 2 electrons fill up that empty outer shell of the hydrogen ion, and therefore we create this coordinate covalent bond. We can get rid of the 2 dots and put the bond in there, and now we have the ammonium ion. So keep in mind the difference between the Bronsted-Lowry definition and the Lewis definition for acids and bases. So here we have hydrochloric acid donating a proton. There's that proton it's donating. It's going to donate it to the water molecule. And now the water molecule, instead of it having 2 hydrogens, is going to have 3 hydrogens plus the charge from the H plus in the hydrochloric acid. So because the acid is donating a proton, this would be the Bronsted-Lowry acid, which makes water, in this case, the Bronsted-Lowry base. And being a strong acid, this is going to happen 100%. Acetic acid, on the other hand, is going to be much, much weaker. I think it's about 3% of these molecules will actually split up. 3% of these acetic acid molecules will donate the proton. Notice how we put that proton off to the end. I actually don't like drawing it that way. I would prefer drawing it CH3, COOH, where here's my first C with the 3 hydrogens. Here's the second C with the double bonded oxygen. That's that one. And then here's my OH, because it's always this hydrogen in the hydroxyl group that gets donated. This is the hydrogen that's going to get donated, and that's what they drew there. That's the hydrogen that gets donated, and so it loses a hydrogen and ends up this, and the water picks up the hydrogen and ends up this. But of course, only maybe 3 per 100 acetic acid molecules actually do that. Now, you can also have diprotic acids and bases as well. Di, of course, means 2. Protic is short for protons. So you can lose 2 protons if the conditions are right. So if you take some sulfuric acid and dump it in enough water, every sulfuric acid molecule is going to donate 1 of its protons to the water molecule, and it's going to keep 1. And so you're going to have the bisulfate ion, also known as the hydrogen sulfate ion, and your water, which picks up a hydrogen, now becomes a hydronium. And that's pretty much all that happens in water. Now you have to force the reaction to continue to go to the right, because once all of your sulfuric acid molecules have done this, it comes to a halt. You reach an equilibrium. That's why you've got the double arrows right there in the middle. you reach an equilibrium. But if you want to drive the reaction to the right, you got to employ Le Chatelier's principle. And in employing Le Chatelier's principle, you can begin to make the HSO4 lose the second proton. And when it loses the second proton, you end up with no protons with your sulfate ion and some more hydroniums. But that requires you to do a titration, to continue to force the reaction to go to the right, to remove the second of the two protons in the sulfuric acid molecule. And here's a further discussion of the hydronium ion and their explanation for why sometimes we simplify it and sometimes we don't. Here's ammonia as a weak base, and meaning it's much, much less than 100% ionized. And in this case, my base is going to be receiving a proton. So therefore, in this particular case, when we put ammonia in water, when it receives a proton, it's a Bronsted-Lowry base, and water is acting as my Bronsted-Lowry acid. And we get the ammonium ion and the hydroxide ion. And of course, if you have a solution of this, let's say you're at equilibrium, and you have a solution of this, it means you have all four of these species in water. All four of them are there. This is not what makes the pH greater than 7. This is what makes the pH greater than 7. Remember, all four of these are in solution at the same time. One is at equilibrium. And whether the pH is above or below 7 depends on the presence of hydroxides and hydrogen ions. By the way, ammonia can do either. Ammonia can either donate a proton or it can receive a proton. So ammonia can act as a Bronsted-Lowry acid or it can act as a Bronsted-Lowry base. When it acts as a Bronsted-Lowry base, you get the ammonium ion. When it acts as a Bronsted-Lowry acid, you get the amide ion. And you see this a lot in biochemistry. And incidentally, the water molecule kind of can do that as well. If we have H2O, you can get H3O when you gain a proton, but you can also get OH minus. Instead, we write it OH minus always. We never do HO minus. We don't do that. But when you lose one, it can go the other way. So water can be a Bronsted-Lowry acid or a Bronsted-Lowry base. We say it is amphiprotic. It can either gain or lose that proton depending upon what the other chemical is that you've mixed it with. Now, reactions of acids and bases, as we said before, an acid plus a base makes salt and water. And as long as that reaction is going to the right, the reason it goes to the right is because you were making a water molecule. And water molecules have that strong bond. That's a strong bond. Only about 2 per billion water molecules are going to dissociate in the purest of water. In other words, water molecules, if you have pure water, only about 2 water molecules per billion will get auto-ionized into hydrogen ions and hydroxide ions. And with that observation, you actually can derive the pH scale, but that's for a later lecture. And when we do our net ionic equation, we can take our hydrochloric acid, and whether we use H plus or H3O plus, if we only used H plus, we'd get rid of one of these waters in order to have our balanced equation. In any case, you have a strong acid, so you completely dissociate it. Strong base, completely dissociated. Strongly soluble salt, SSS, strongly soluble salt, completely dissociated. Water, molecule with a strong bond, you cannot completely dissociate it. You've got to leave it intact. like you do with all weak acids and weak bases and weakly soluble salts. And then when you go to find your ions that cancel out, the ions that are going to cancel out are going to be your chlorides, spectator ion, and your sodiums. And once again, like we said earlier, your net ionic equation is hydronium plus hydroxide produces 2 waters, or hydronium 1 plus hydroxide produces 1 water. It doesn't matter which one you use unless you have a professor who has a preference. That's always the net ionic equation, assuming you have enough water to completely dissolve everything. Sulfuric acid, just a little sidebar here, that sulfuric acid is one of the largest quantity. It's produced in greater quantity than just about anything else in all industrialized nations. This is sulfuric acid, because so many things can be done with sulfuric acid. One of the things that can be done with sulfuric acid is you can react it with lime, calcium oxide. Sometimes people, if their soil is too acidic, they'll put some lime on the soil to kind of sweeten it, which means to neutralize its basicity. And in any case, if you combine calcium oxide and sulfuric acid, you get calcium sulfate. And this is what drywall or wallboard is made out of. You go around your house, go around the school, go around just about any business, and you see millions of square meters of drywall all over the place, on walls, on ceilings. It's just the ordinary, very inexpensive, easy to work with building material. But by far and away, most of your sulfuric acid right over here is going to be used in the fertilizer industry in order to either use ammonia or other fertilizers directly on cropland in order to increase the yield, but it's also used to make pigments and adhesives. It's used in the paper production industry. I know when I visit my wife's family or her sisters up in northern Wisconsin, we go by a lot of paper mills. They have a lot of trees up there to get the pulp. Detergents, storage batteries, your car batteries often have sulfuric acid in them. We call these reactions neutralization reactions because the acid and base are neutralizing each other. And if we're going to do our net ionic equation, just as a quick review, here we have acetic acid. And again, I don't like the way they write acetic acid. I would prefer writing it like this, which is how the inorganic chemist would write it, or to write it as the organic chemist would, CH3COOH, where the first oxygen is the double bonded oxygen, the carbonyl or carbonyl, and then the hydroxide we keep together. And this is the hydrogen right there that gets donated. It's never the hydrogen connected to a carbon that gets donated. It's always the hydrogen next to the very, very electronegative element like oxygen or sulfur. And so here we have acetic acid. And one reason I like this drawing here is because you can see the positive ion and the negative ion. And you can swap it with the positive and negative to get your positive and negative over here, and then you get your water molecule. So step number 1, we want to write the balanced equation. Step number 2, we're going to march through all 4 species 1, 2, 3, 4. And again, I'm using the word species, not like they do in biology. When I'm going to march through all 4 of these and take apart the strong acids, the strong bases, and the strongly soluble salts. So I look at acetic acid. It is a weak acid, so I don't take it apart. I look at sodium hydroxide, strong base, take it apart into its ions. I look at sodium acetate, strongly soluble salt, take it apart. I look at water, I can't take it apart because it's not a strong acid, it's not a strong base, it's not a strongly soluble salt. It's got a strong bond between the hydrogen and the hydroxide that's keeping it from being able to be yanked apart. To yank apart water, you got to break that bond. You got to separate it, and that only 2 per billion will do that in pure water. So it's a rather strong bond. It's hard to break. And so then when I cancel out my spectators, you can see that my sodiums cancel. Remember, you only cancel ions. You never cancel out something that is not an ion. And these are the only ions that are present on both sides. There's nothing else to cancel. So here's my net ionic equation in step 3. Here we can do a net ionic equation with a weak base. And we have our weak base here. We have a strong acid here. And you should know the product of this reaction. A good AP test would not tell you ahead of time what the product is going to be. A lot of times it's helpful to, in fact, it's essential that you remember that you're in a aqueous environment. You've got a water environment here. And so the water, the polar water molecule can yank the hydrogen away from the chloride. And this hydrogen is going to be picked up by the ammonia, and by the ammonia becoming the ammonium ion, which is positive ion, and the chlorine, which is left behind, is your negative ion, and they would attract each other to make ammonium chloride. But of course, this is in a water solution, and polar water will just yank them right apart again because this is a very, very soluble salt. So when you go through this equation in step 1 and separate the things that you can separate, you can't separate the ammonia because it's a weak base. You can separate the acid because it's a strong acid. You can separate ammonium chloride because it's a strongly soluble salt. And you can't separate the water. So when you cancel out your spectators, which are the chlorides, here is your net ionic equation. Now we can also make acids and bases using oxides of nonmetals and metals, which is something that we talked about earlier in this chapter. The oxides of nonmetals would be, you take a nonmetal from the right side of the periodic table, not counting the last column, which are the inert gases, and you take one of those oxides and you combine it with water. For example, carbon is a nonmetal, and so carbon dioxide is an oxide of a nonmetal, and you combine it with water and you can make carbonic acid. And so when you bubble carbon dioxide through water, you reach an equilibrium. And so you have all 3 of these things in water at the same time. If we talk about a closed container like a can of soda, you're going to have carbon dioxide in there, you're going to have water in there, and you're going to have H2CO3 in there all at the same time, as long as this is a closed container. And it's going to be in equilibrium. Now, keep in mind, of course, that your carbonic acid, to whatever extent is possible, under pressure at that temperature, will turn into some more water and some CO2. In other words, it could go a little bit back again, but it's going to reach an equilibrium, in which case it's going left and right at the same time. Now, as soon as you pop the lid, and so we're going to pop the lid, there's the green opening, and now what's happening when we pop the lid is the carbon dioxide is escaping. And when the carbon dioxide escapes, then the reaction can keep going to the right. And if you think about it, as the reaction is going to the right, you get less and less carbon dioxide. It goes down. And so your soda tastes flat, bland, because the fizz is gone. And as you create more and more water to go along with the water that's already there, your soda tastes watery. It tastes more dilute. Also, some companies will package their can of soda under much higher pressure. There would be a little bit of headspace at the very top of the can when it's closed, where they'd have as much pressure as they want to put in there. I think, what's the name of that soda? I can't remember it now. It's a local soda that has 1,000 bubbles and a lot of fizz. Now, let's continue though. As we make this carbonic acid, the carbonic acid is also going to continue to react if the reaction is going to the right. If we enable the reaction to continue to go to the right this way. And so when I'm making this and it continues to go to the right, pretty soon I get bicarbonate ions and some more hydronium ions. And then if we allow it to continue to go to the right by stressing the reaction, Le Chatelier's principle says now you're going to donate the last hydrogen. You already donated the first hydrogen. Now you're going to donate the last hydrogen. Now your carbonate doesn't have any hydrogens left, and you've produced even more hydronium ions. You've made it more acidic. And so there are other examples of non-metallic oxides like sulfur dioxide, like sulfur trioxide, like nitrogen dioxide. And you'll notice that in every case, you are making acids. So these non-metallic oxides can make acids. Oxides of metals can also make acids. And here we have lime, calcium oxide. Calcium is a metal. So this is a metallic oxide. We combine it with water and we get calcium hydroxide. And you'll see the hydroxides, which means this is going to be a basic solution and the pH is going to go up above 7. So those are all very good examples. By the way, let's look at this reaction in reverse. Here is my metallic hydroxides, and you might remember the pattern, the mantra that you were supposed to memorize in first year chemistry, that metallic hydroxides decompose to form metallic oxides and water. So here's a good example of a pattern that you memorized written in reverse. And just like you would be expected to know that metallic hydroxides decompose to form metallic oxides plus water, you would be expected to know the reverse of that reaction as well. And you can review and check here for yourself. It says, which of the following was a strong acid? That would be very, very easy because if you memorized your 6 strong acids, there's only one in the list. What about something that is amphiprotic, that can either gain or lose a proton? And so you, for example, H2PO4 can gain 1 to become H3PO4, or it can lose 1 to become HPO4 with a 2- charge. By the same token, the same is true here. HPO4 can lose 1, becoming the phosphate ion, or it can gain 1 to go back to the dihydrogen phosphate. When we talk about what is the net ionic equation in number 3 for the reaction of acetic acid and sodium hydroxide, you would recognize this is a weak acid plus a strong base. It's going to produce a salt plus water. You would rule this out because you have a weak acid. You also know that sodium acetate is very, very soluble. All of these are aqueous. Those potentially would be spectators. When we come down here in letter C, here's my acetic acid. My sodium has been dropped as a spectator ion, and so I get hydroxide, and my sodium acetate leaves behind the acetate ion, and my hydrogen hydroxide become water. And so if you think about where the water came from, it came from here and here, made this. So that is a very good possibility. We would rule this one out because we do know that if I have this is a weak acid, so I probably shouldn't put it in aqueous, it should be liquid. This is my strong base, and this is a strongly soluble salt, we would expect that the strong base and the strongly soluble salt would dissociate and the sodiums would cancel. And then in number 4, if you remember that metallic hydroxides decompose to form metallic oxides in water, therefore barium hydroxide, when reacted with water, is going to produce a base. So this would be a basic oxide. Barium hydroxide is a basic oxide because it makes a base in water. And here's the base. So here's some examples of gas-forming reactions using other metal salts. And then one down here using an ammonium salt. Now, the other part of the screencast is about gas-forming reactions. We do have gas-forming reactions that are not double displacement or exchange reactions where they exchange their partners. In this particular reaction, you have calcium carbonate and hydrochloric acid. And you should know that calcium carbonate is a very, very common non-soluble salt, +2, -2, extra strong charges holding them together. But they are both ionic compounds with a positive and a negative. This is a strong acid, so it is going to dissociate. We're going to have a strongly soluble salt that will dissociate, and your carbonic acid immediately breaks up into water and carbon dioxide in this open system. It's open to the air. So you wouldn't even put the carbonic acid in here unless you were asked to do it. And you would immediately write its products as being H2O and carbon dioxide, gas and liquid. And so you can see why this reaction is going to go to the right. That even though this is a solid, when you put acid on it, the reaction will go to the right because you're producing carbon dioxide gas, which is escaping into the environment. And Le Chatelier's principle says that when you remove one of the products, the reaction will keep going to the right as long as it can to replace the carbon dioxide that has been lost. And will keep doing that until you have no more calcium carbonate or you have no more hydrochloric acid, depending on which is your limiting reactant. And so your net ionic reaction is right here, and you'll notice that there really isn't anything to cancel out, so there are no spectator ions, no couch potatoes that are just standing around or floating around watching. Now, by the way, when we look at this reaction, let's see, coming down a little farther on the page, talking about baking. Sometimes we use yeast when we bake. Sometimes we use baking soda and baking powder. But what makes the cake rise, the bread rise, the muffins rise, the cupcakes rise from the dough is the production of a gas. If you're using yeast, yeast is a kind of fungus. It's like a mold. It's a organism that is going to undergo cellular respiration. It's going to feed on sugars, and its flatulence, hopefully this does not make bread less appetizing for you, its flatulence is carbon dioxide. Just like you exhale carbon dioxide as a result of the food that you've eaten being digested, the same is true for yeast, and that carbon dioxide is what makes the bread to rise. If you're not using yeast, but you're using baking soda, you get the same kind of thing. Your baking soda is going to react with whatever acid might be in your whatever it is that you're making. For example, if it's something that has tartaric acid in it, tartaric acid is a weak acid, and you put in your baking soda, which would be sodium bicarbonate. Notice that the sodium ions have canceled out. The sodium bicarbonate and the sodium tartrate, the sodiums cancel out. And so you're looking at the net ionic equation here. The tartrate ion is not an ion that you would be expected to memorize unless, of course, you're going into a specialized field of biochemistry. And so you have your chemical reaction going on that produces carbonic acid, and your carbonic acid immediately decomposes into water and carbon dioxide. And the carbon dioxide is what's going to cause this your batter to rise and become fluffy. Here's another example of a reaction that's going to produce carbonic acid, which decomposes into water and CO2. So you can see these gas-forming reactions are often a double displacement, or sometimes called an exchange reaction, because they're exchanging ions. Your double displacement reaction, and it's also a decomp reaction, because one of your products, that is carbonic acid, decomposes. And I'll leave this review and check for you to do, and the answers, of course, are in the back of your book.